Alrighty, simplifying radicals. Now, this is oftentimes the bane of people's existence, but it's really not that bad. Okay, what it comes down to, we talked about this already. This is a good one here. If you have different bases underneath, you can write them as separate factors. And then we talked about that one last section. It's nice to be able to break things down because you can simplify them better. Now, simplifying with radicals is you're looking for redundant pieces inside the radical where the factor is a perfect square. So if you look at root 20, well, 20 is 4 times 5. And writing that is exactly the same as writing the square root of 20, because 4 times 5 is 20. And then we use this rule here, this property, to rewrite it like this. But then the square root of 4, we know it's 2. So you can write it as 2 times the square root of 5, and that is simplified. Now, the other way to think about it is, remember that any time you find, if you're dealing with a square root, 2 identical factors, they team up to escape, right? So like here I have 2 identical factors, and they just become 1 on the outside. Now, why do I make a fuss of that is because if you're dealing with variables, it's a little bit trickier to witness, a little bit trickier to make sense of, but let's look at a few examples here. So cube root of 24, which means you need 3 identical factors, or you need to know your cube roots. So if you just think about cube roots, it's 1, 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. Those are perfect cubes. So you're trying to find factors of that. Now in this case, yeah, 24 is 8 times 3. And the cube root of 8 is just 2. So again, simplified. But you see, breaking it down, 1, 2, 3 common factors, they come out, and they just equal 2. That's what we're doing when we simplify. We're pulling out factors that don't need to be in there, right? They are a perfect cube, or they are a perfect square, or they are a perfect fourth. Why are they in there, right? They don't need to be, so we simplify it. So now look at this thing. First thing to identify is dealing with a square root. So we're looking for 2 identical factors. And what helps is break this down. Now I broke it down below in fewer steps, but 180 is 18 times 10, which is 2 times 9, which is 2 times 5. Now I'm not even going to break the 9 down any further because that's a perfect square. And then I have a 2 and a 2. So that means what's coming out? A 2. See, there's your 4 and your 9. So a 2 comes out, a 3 comes out. And what stays underneath the radical is just a 5, because that's the only number left. So that simplifies the 180. But now x to the 6, we can look at this a few ways, okay? X to the 6, is it a perfect square? Well, think about, can you write x to the 6 as something squared? And you can, if you think about your exponent laws, that's x to the 6. So if that's under a square root symbol, those things cancel, and what comes out? X cubed. So before we put the radical down, has anything else come out? Yeah, an x cubed has come out. And then if you look at your y, this one's a little bit, you can't do the same thing I just did there, but y is y cubed. Well, that means you have y times y times y. How many do you need to come out? You need 2. So those 2 pair up and leave, come out to the front, and what's left on the inside? 1y. So overall, what's left on the inside? A 5 and a y. So it's 6x cubed y root 5y. And this is a typo. I have to fix that. These are going to take practice again. So please don't be upset if right away you're like, whoa, what's going on here? So if we look at the next example, this is when it's really helpful to break the large radical down. So you'll see we went from the cube root of everything to the cube root of each term. And then we simplified. Now x to the 12 is x to the 4 cubed. Cube cancels with the cube root. You're just left with x to the 4. The cube root of 64 is 4. You're done. So that's going to take practice. And don't think that I take this lightly. In the book, I only give you a few examples, but we'll do more in class. So be prepared for that. Now, going from a mixed radical to an entire radical is when we go back in. So just think, if you have 1 out here, how many did you need to have before it could come out? 2. So there's 2 when it goes back in. Now this was a grade 10 piece as well. Now here, this goes back in. This cannot, right? The negative stays out front because you can't bring a negative out of a square root. So now when this goes back in, how many 4s? 2. How many x squareds? 2. Then you can multiply all the whole numbers together, all the x's together, and it builds back to where it was. 2 more examples. Have a look through those as much as you like. You'll see that this goes back in as a fraction because the 5s are denominators. That's why we end up with a denominator in our fraction or in our radical. And here's practice. So I'm going to do a couple of these for you. Simplify. I'm going to do this one because it's probably going to piss you off. Tens, hundreds, thousands, 10,000s, 100,000s, millionth. So you actually have 64 over 1 million. And you're looking for the 6th root of that. Well, 64 breaks down to 8 times 8, which is 2 times 4, 2 times 4, 2 times 2, 2 times 2. 1, 2, 3, 4, 5, 6. So what's the 6th root of 64? It's 2. And then what's the 6th root of a million? Well, take a guess. 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0. 10 to the power of 6. So 2 over 10, which simplifies to 1 over 5. A little tip for you, 0.04 is 4 over 100. And the rest of this, now, you'll see here there's a negative inside the radical. Why is that allowed? Because it's an odd index. If that was an even, you wouldn't have a negative in. Can this negative go back in? Yes, it can, because that's an odd number. So look for that. I'll let you work through the rest, and yeah. Okay. Again, this is practice of simplification. Don't just go through these quickly. Make sure you truly understand what's happening.